Okay, folks, welcome to Module 3, where we're going to be talking about debugging, assembly, computer architecture, and we might get a little bit into operating systems, but mostly focusing on debugging and assembly here. Okay, so the video will be posted here, and then just a little bit on the readings and warm-up as well. Okay, so let's go ahead and dive right into it here. Okay, so just a fun pre-warm-up for us, and we're going to be talking about another language today, assembly language, just so that you get the full view of how code gets compiled from C and eventually becomes an executable on your machine. But you can learn this by playing video games, which is kind of cool. So Zachtronics, which is a studio, has a couple of games, Shenzhen IO being one of them, where you get to play a little bit as a hacker, learn some electrical engineering, which is pretty cool, but also some assembly language to beat some of these challenges and become a hacker. So there's some fun games like that if you want to supplement your learning, if you really enjoy today's topic. Okay. So let's go ahead and get started. So just logistics, your homework too. Look on the course schedule for the due date that's coming up. And then make sure, again, you're testing on the Cori systems and writing your code on the Cori systems, just because that's what we'll be using. And again, check your GitHub to remember that that's what we see. So whatever is on your GitHub. So if I go to my GitHub page here, let me go ahead and do it here. Whatever we see on your monorepo hyphen your name is what we indeed see. Okay, so just make sure that that's pushed, or if you have any questions about if it was pushed successfully, you can always check that. Okay, so what we're going to, or where we've been in this class so far, has been talking about the C programming language. So we've explored concepts of memory, just this idea that it's a large grid and how memory gets allocated on the in this sort of linear grid here, and then how we use things like malloc and free to put memory in the heap, and that we need to manage that memory. We've learned about C being a pass-by-value language, and some of the other sort of syntax of the C language and its capabilities. And then we built a data structure, a linked list data structure in the lab, and you're working on the queue and stack for your homework. So we're kind of just diving right into this. Okay, so something I just want to add at this point too, from where we are, particularly on C programming, this course tends to start off fast. So C is a new language, and things like pointers and building the data structures from scratch is something that we know is difficult, and it's difficult because it's new. So just want to, your instructors and course staff understand this. So it's not abnormal at this point in the semester to feel a little bit overwhelmed. So we've tried to provide as many videos and so on as we can to help you, but again, I understand it's just going to feel a bit overwhelming, and that tends to be normal. But the things that you can do are just keep practicing C, keep powering through it, coming to the office hours if you can, or just reviewing and experimenting. Our goal is to really push you a little bit, but not to the extent that it's extremely difficult. So we are aware of this. Just be a little bit patient and keep practicing your C, keep trying things, asking questions, and you'll get through it. We always get everybody through it. So this course tends to start off difficult because of the C component, but eases up a little bit once you get a handle on the language. So just a note on those folks who might want a little word of care or a little word of encouragement. Okay, so where we are so far, again, in the semester is, we're learning how to operate in a new environment. Terminal, Linux, which might be a new operating system for a lot of folks, working through SSH remotely. So all great skills to be developing. Again, we're learning the language C, again, and some of its new capabilities, things like pointers. Even though you didn't have to use pointers previously in a language like Python or Java, they're still there. They're just hidden from you. So C kind of exposes things at the, at a very low level for you, which is nice. Okay, so you have that control. But again, it's new, so it's going to take a little bit of practice. And we're also learning about different data structures. So we're almost building a toolbox at this point of different data structures that we can use to build bigger and more powerful software. So things like the linked list, queues, and stacks, for instance. Okay, and we want to learn about these data structures so that we can build larger programs, build more interesting algorithms. So we got to get our foundations first, and that's really the first part of this course, so building our data structure toolbox. Okay, so a little note for you is that low-level programming is good for the programmer's soul. And this is a fun quote by John Carmack. So if you don't know who John Carmack is, here he is, this gentleman here. He's known primarily as a computer game programmer for the games like Doom, Wolfenstein, Commander Keen, and built some sophisticated, game engines that were used to build these games. So really a kind of cool programmer in that he was also one of the first to start open sourcing a lot of his stuff so others could learn. So again, someone very, very smart, but wanted to share with the community about some of these games. So to this day, you can look up what the source code looks like if you're curious. I believe at this time he's still the CTO of Oculus, which was something that he was working on, and then they got acquired by Facebook, and sort of working on virtual reality stuff. So he does some cool stuff, and he's going to convince us that low-level programming is good for the soul. And I'm just going to add to that, it's just nice to know how it all works sometimes. We want to sort of dispel any of the magic going on in our machines and just, become low-level programmers. So what we need to do today is, continue looking a little bit deeper into our environment and looking at it from the perspective almost of an instruction. And by instruction, I mean a line of code, and then an individual, piece of that code even. So very fine granularity of what happens when we're executing an instruction in our machine. Okay, folks, so let's talk a little bit about operating systems. So the operating system is a manager of everything that we do in our machines. We've talked about that a little bit before, about how it's our resource manager. So there's software inside the machine. That's the operating system that you install. That's keeping track of how everything's running, how many programs are running, the files, and everything. Okay, so we've previously given our operating system this name of resource manager. And there are, specific resources that it manages, like the user, that's us, or many users if we're sharing a machine. Of course, all the applications that are running and the hardware. So if you ever plug in a mouse or a USB drive to a machine, it also has to know how to interact or interface with that hardware device. And here's another view of where operating systems lie in the grand scheme of things. So we're the user, we run applications, we have our operating system, and it sits in between the hardware. Okay, so here's perhaps another view of it. We're the user, we're going to write our applications in C, then we'll run those applications. That's what happens when we do /program on our terminal. And then the operating system will load that application into memory with all of its instructions, all the lines of code that we said to do something with. And then it's up to the operating system to send those instructions between the hardware, that's your CPU and sort of the low-level microprocessor and all those things that we'll get into. We'll understand how to execute those instructions based off of the operating system's communications. Okay, and our operating system, does this task of loading and running programs alongside many other things that's doing, like the resource management. But something that we're interested, or at least that I'm interested in giving you a sneak peek at, is that operating systems, for instance, will keep track of all of your files and all those functions that we're using in C, like fopen, fclose, fread, fwrite, and so on. The operating system is actually using these functions to interface with its file system that's built into it. Okay, so it's managing all the different files, that data file, a photo or a video that you took, and sort of organizing them. And there's a little dirty secret in Linux that everything in your operating system is actually just a file. So even if you plug in a mouse, that's seen as a file. If you plug in a keyboard, that device is seen as just a file. A hard drive is just a file. So all it really sees is just collections of bits that are sort of neatly organized in our operating system. So I just want to give you a sneak peek because it's relevant to linked lists, which is one of the data structures that we've studied previously in our lab and that you've implemented. And linked lists are used everywhere in our operating system. There's a specific struct for it called inode. And if you look at this thing, it's a little bit intimidating, but you can see how big these structures get. We don't need to know everything about it, but we just need to know it has the name node in it, so that gives us a hint that it's a linked list. And if we look carefully at some of the different fields in this structure, we see that there are next pointers and previous pointers, for instance, so pointers to other nodes. And this sort of makes sense that we would have a bunch of files organized on our system as a linked list because, well, if you've been using a computer, you know that you create files and you remove files and you move them around. So that's something that we can do with linked lists very neatly. We could just sort of move the pointers to point to new things or remove nodes by just calling free on them. So just like we remove files, it's the same thing. Just behind the scenes, it's implemented now that you know as a linked list. Now there is something interesting about this particular data structure here in that node is, well, there's a next, and we used next before, but as I mentioned, there's a previous to our node. So previously we only had next, so we could only move in sort of one direction in our linked list. So that was something that we hadn't done before. So what I want to talk about is a new data structure, which is called a doubly linked list. And this is a data structure very similar to a linked list, except that it has a previous and a next node. Okay, so here's an example of the structure here. So we just have a node here, some data, and a node to the previous node. So if it's at the head of your list, it just is null because there's nothing in front of it. Then we traverse to the next pointer here to the next node. And then our next node will always point back to, well, the previous node in this linked list or this chain. And then likewise, this continues, and then our tails last next node is null here. Okay, so it's always helpful to try to draw out these data structures just to help understand them. But again, all we've done is added another pointer to our node so that we can point to two things instead of one. In this case, the previous node, if one exists, otherwise it's null, or the next node. Now, we want to think about this a little bit, but does the big O analysis of this data structure change? That is, how long does it take for me to insert something or remove something? Well, for a doubly linked list, if you want to go ahead and pause the video and research big O on this data structure, go ahead and take a moment to do that. And if you're just joining back with us, the complexity is actually the same. If we're going to add a node to the linked list, we can quickly append a node or prepend, if we're starting at the front of our list, a node, and do that in constant time. It's just moving in one pointer for our node. So that can be done in constant time or just one operation. If we need to search for a node, we have to look and sort of iterate through every node. So look at the next node and then the next node, one after the other, and that would take O of n time. That is the number of nodes that we have, O of n, is how many we potentially have to, in the worst case, look through to find something, okay? Again, we're going to get into big O in a little bit more detail in this course, but just something to be thinking about with these data structures. How long does it take to add something or remove something or search for a piece of data? Okay, so with that, I want to talk about debugging a little bit. Okay, so I've given you a new data structure, and I want to show you a tool that's very helpful for working with C code. And this sort of goes to the earlier message in the lecture about just learning C and getting a handle on it. C can be difficult to learn, as mentioned, but we have tools to help us. So when you think about it, the C language has been around almost 50 years at this point. So during this time, programmers like you and me have said, hey, C can be difficult sometimes, so can we build tools to help us? And one of the tools that was built is called a debugger. So debugger, or rather the art of debugging, is the act of interactively investigating how your program is behaving. So we debug our programs usually when we discover that an error occurs. And there's different ways to do this. You can do it in sort of an ad hoc way where you just print out a value and inspect it, okay? But there have been other tools designed to help us. Okay, so we sort of have this way that we can do things. So I'm going to just write a little program here to show you the simplest way of debugging. And I'm just going to call this main C. And oops, it looks like I already have a main C. So I'll just delete this here and create a new little program here. And let's include our standard IO library. And let's just create a variable x, and I'm going to assign it a value 7. Now, if I run this program, it's not going to do anything too interesting. I'm going to run it with -g, which will become important for our debugging. Any warnings that might occur, so W, capital W for warnings, in all of the warnings possible, and then our program here. Okay. And we do get a warning here that we have an unused variable, but that's okay for this example. I'm just going to go ahead and run it. Because we don't really know anything about this program, but again, remember, debugging is this sort of active, interactively investigating how our program is behaving. So a really simple way of debugging would be to print out the values here. Okay, so %d, and then because this is an integer type, a new line, and then the value of our program. So this would be a simple way to debug the value of x at this point in the program. Okay, so this is a technique called printf debugging. So we can just get the value here. And usually I like to put a little helpful message here. X is, just so we know what it is here. Okay, so again, printf debugging is a technique that we can use, but there's been specific tools that are going to help us. So here's just a little aside on printf debugging that might be useful to have, right? You can always sort of do this trick and recompile and print something out. Sometimes it's helpful. But again, folks have built this tool called GDB that's really helpful for interactively debugging our programs. Okay, so I'm going to do this with you as sort of an exercise. There's some videos on Canvas as well showing how to debug. But just to show you, again, how to sort of build a program from scratch and a doubly linked list. Okay, so again, the idea of the debugger, though, is that it shows us what's going on inside the machine. So again, the debugger gives us this unique perspective into what's going on in the machine. And in fact, you can actually see the ones and zeros in our machine once we learn a little bit about assembly later. Which is actually pretty cool, because then there's really no secret to what is going on. Okay, so there is a cheat sheet in your repo on some of the commands that I'm going to show. There's also going to be a resource at the top of your readings for some debugging so that you can practice, and of course you've got these videos. So let me go ahead and show you a live debug of building a doubly linked list here. Okay, so what I'm going to do is I'm going to restart this here, and let me turn off this program here, and we'll just start from scratch here. And I'm going to write it, I'm going to call it called doubly.c, and our goal is to write a doubly linked list. Okay, so sort of build the data structure and just see what it is. We want to get a little bit of confidence here, just sort of being able to dive into code and build it from scratch, which is a skill here. Okay, so we have our main entry point into the program. Okay, and let me just review quickly again what the doubly linked list structure looked like. And it looked like this. We had some node, some data that we want to carry, and then a structure to the previous, to the next, and the previous node. Okay, so that's what we're looking at here. So let me go ahead and put this here. So let's go ahead and create that structure here. Okay, so I have a struct here, a node, and I'll actually leave this lowercase like this, and some data, and then we have a struct to a node that is our next node. Now these are pointers also, remember, so we have a star here, and then a struct to another node, that's our previous, okay? And I'm gonna hit escape, :W to save the file, Control B to move over, and again, just compile this code again, because I want to save and compile often, just so if I've made a mistake, I can quickly fix it while there's less code here. Okay, so I'm going to run gcc doubly.c, and then output, I'll just call this doubly again. And let's actually add with -g our debugging symbols, because we're going to get used to debugging. So this adds extra information to our program when we compile it. Okay, and let's add any warnings as well. Okay, so it is still compiling, so we can continue on. Okay, so just very simply, this node structure will allow us to build a doubly linked list. Now let's build a little bit on top of it and create something doubly linked list here. Okay, just to add a little bit more power here. And we want it to consist of a head and a tail node in our doubly linked list. Okay, and let's make this a little bit easier to use, so we don't have to type out struct every time. We can use the typedef keyword, and that'll sort of combine type struct and node, and then we can just type it out as node underscore t in our program. Okay, so in our doubly linked list, we'll have node t and the head, and this is a pointer, and we'll have node t and the tail, which is the end of our doubly linked list. Okay, and let's also include maybe the size or the count. Okay, and this is going to be the number of nodes in our doubly linked list. Okay, so we've got our basic node here, and then we've got the data structure, which is going to hold the first node and the last node. Okay, now let's go ahead and give ourselves the standard IO library. And we're going to be allocating some memory. So I need the standard lib where the malloc and free functions live. Okay, so this is for malloc and free, and this will be for standard IO functions like printf. Okay. Now let's do something a little bit interesting with our doubly linked list, like create a function to create list. Okay, so create doubly linked list. Okay, I'm going to write it like this, and it needs to return a doubly linked list. Okay, and I'll make this a pointer because we're actually going to allocate some memory. So what we should do here is allocate a doubly linked list. So the type needs to be a doubly linked list. Okay, and this is also a struct, so I'm going to use the typedef keyword here. And let's see, let's call this just DLL underscore T for short here. So then I can just create this as DLL underscore T. Okay, and that'll be our return type. DLL underscore T. So that's the exact same thing as writing out struct doubly linked list every time. So I've just saved myself a little bit of typing here. Okay, so we're going to create a node. I'm just going to call it, or rather create a linked list, new list, and we need to allocate memory for this linked list. So it's type of pointer, malloc, and however big our doubly linked list is. Okay, so the size of one of these lists. And the size of this list, again, it contains a pointer to our head, a pointer to the tail, and the count. So however much memory that takes, that's how much we're allocating here. Okay. And once we have our list, we probably want to initialize it to say the new list and one of its fields, which we have the head, is going to be null, and the new list, the tail, is going to be null because our list is empty. Okay. So let's go ahead and start with that. And let's go ahead and set the count, okay, to 0 because we have nothing in our doubly linked list. Okay, and let's go ahead and actually create a new doubly linked list here. So we have a helper function that we've defined to do this, and it'll return a pointer to our node here. Okay, so we actually have to return this pointer here. So return our new list. So this is of type pointer here. We'll return the new list from our doubly linked list here. Okay, so here's a new list. I'm just going to call it my list here, and it's a doubly linked list, and set it equal to create doubly linked list. And every time that this function's called, it'll allocate a new list for us and return it with the head, tail set to the sort of default values and the count here. Okay, and then before I forget, let me try to or make sure I free my doubly linked list so that there's no memory leaks. Okay, so at this point, again, I've typed in quite a bit of code. Make my window a little bit bigger so you can see everything. We should also save, compile, and run again. Okay, so I saved. I will compile. Oops, looks like I made an error here. So I forgot a semicolon. I'll save again. Recompile. I want to do it with the debug symbols every time. And go ahead and run this program here. Doesn't do anything right now, but that's okay. So one thing that we could do also at this point, just to make sure that our memory is being freed, is run Valgrind with this program. So if I run the program doubly, I can see that all the memory that I've allocated has been freed here. So it's going to say in use at exit. Well, there's 0 bytes. Okay, so total allocations that I've done, 1 allocation. That was here when I created this doubly linked list here. And I have 1 free, which I did here. So for every allocation I do, I should have the equivalent amount of frees here. 24 bytes were allocated. So in this case, it was probably 8 bytes for the head, 8 for the tail, 4 for the count, and sometimes it will add an additional 4 bytes to get this at a nice sort of round number. So that's why it's probably 24 bytes here for this structure. Okay, so no memory leaks. Okay, so we've got a doubly linked list. It doesn't really do anything that useful right now. So let's create another helper function to add a node. Okay, so we will call this add node, or perhaps add DLL node. And it needs to take in a doubly linked list that we're going to be modifying and the head of that list. And we will add to it. Okay, so how do we want to do this now? Well, we're going to take in our doubly linked list and decide if we want to add at the end or the back of the list. I'm going to go ahead and say, let's call this prepend DLL node, which implies add to the front of the list. Okay, so that means we will change where the head pointer is. Okay, so what do we need to do? We need to create a new node. Create a new node. And then we need to move the old DLL pointer, or the old DLL, old head prev node, to point to this new node. Move old head prev node to point to this node. Okay, and that's it. Okay, so let's go ahead and create our new node. And this is just a DLL new node. And so I'm going to give it a name as, or rather, it's just a node T. Excuse me, it's not a doubly linked list. And allocate for it the node, the size of, well, however big that node T is. Okay, and let's go ahead and set the attributes of it. So the data, it needs some data. And let's just set it to a number. How about 1? It's a good value to have. Or 7, just something a little bit more unique. In case 1 or 0, those are sort of common numbers. So I like to add, more strange numbers so they'll be easier to identify. And let's set the next and the previous node appropriately. So the new node, the next needs to equal our head, or the head of our doubly linked list. And our new node's prev, well, it's going to be the front of our list, so it's just going to be null. Okay, so what updates do we need to make to our previous doubly linked list? Well, we have our head. That's the node that's incoming. And the previous needs to point to the new node. Okay? So that's the O of 1, or constant, operation that we do to sort of just glue this node to the front of our list. Okay, so we're just resetting that pointer. Okay, and that's it. So we've allocated for our node here. So let's go ahead and run it and try our prepend node function. Okay, and let's see if we've covered all of our bases. So we're prepending a node, which essentially just creates a node with this particular data here to a particular list. Okay, and it's always going to do it with the same data. So let's make this function a little bit more robust and just add a parameter and just say data here. Okay, so whatever the data happens to be. So prepend the DLL node. Okay, prepend DLL node. We have to pass in which list we're going to be modifying. So we're passing in a pointer, which will make a copy of this. But remember, it stores the address of the node that was passed in. And let's change that data here. Okay, so I'm going to try to compile and run and see if I made any mistakes. And oops, looks like I made one mistake here. I've got to modify our node here, because I've used the name a couple of times, and I should fix that here. Let's just call this our list here that we're modifying. Oops, and I've got to then modify this here to point to our lists. Oops, and then our lists head here, because this is our doubly linked list, or the actual node here, will point to our new node. So just a few fixes there, and we should be good to go here. So let me make this a little bit bigger just so you can see all the code here, and then we're going to get to debugging in GDB once we've built our list here. Okay, so let's go ahead and just run this, and looks like it works. But how do we know we're actually adding a node here, especially if we're building a data structure? Well, we could write a helper function that prints off all of our nodes. That would be a good idea. And secondly, let's try running this again with Valgrind, which we're learning to do, and our doubly program. And if I run it, well, this time I see that I've definitely lost some memory because I've done 2 allocations. I've only freed once, and I've allocated 48 bytes total, but there's 24 bytes somewhere in one of the blocks that are in use. Okay, so maybe some of you have spotted the error, but let's go ahead and run Valgrind and see if it can help us find where this error is. Okay, so this is the first part of our debugging with Valgrind. Okay, so I'll run with Valgrind, and it says to run with leak check equals full here. Okay, so I'm going to run leak check equals full, and then run our program doubly again. Hit Control L to clear my screen. And this time it gives us a little bit more information and says, hey, at line 32 here, you allocate, so 24 bytes are definitely lost, and it's able to figure out where. We use the malloc function, and in the prepend DLL node at line 32, we're allocating memory here without freeing it. Okay, so we would need to write a helper function to iterate entirely through this list and delete things. Okay. Okay, so we have Valgrind as a tool to help us, but what if we didn't? What if we wanted to, sort of interactively look through this and figure out some information about what's going on in our program? Again, that's where GDB comes through. Okay, so GDB is the GNU debugger. So let me run the man page, GDB. And it's the GNU debugger. So again, the purpose is to see what's going on inside in the program while it executes. So let's go ahead and see what's going on inside. So run GDB and run our program doubly. So that's how we do this. Now it's important when I've compiled the program doubly that I've used, let me go back here, the -G compiler flag. That gives more information so that when I run GDB, I'll be able to see exactly what line things happened. Okay, so I'm going to just recompile it once again and then run our program Valgrind doubly like so. Okay, now I'm inside. Oops, excuse me, I did that with Valgrind. Let me run GDB and then doubly. Okay, so now I'm inside the GDB debugger at this point. Okay, so what I need to do now is type in run, or just R for short, and hit enter, and that will execute our program. Now this program executes pretty quick, so nothing really happens, right? And we're not really printing anything out here. So we can print out a message in our program if you want. Let's just print one at the end. Ending program. I'll close the quotations. I'll put in a new line here and a semicolon. I'll save. And now I need to quit GDB though because I've made some changes here and I'm still in GDB. So I'll type in quit, or just Q for short. Recompile the program, Control L, and then rerun in GDB. So now I'm running this new version that has ending program. And let's just run it again. This time it says it's starting the program, where it's located. So in my home directory, Mike, and the program's called doubly. And then it ran the program here, just printed out ending program. Okay, so I mean, again, our goal here with the debugger is to be able to peek inside and see what's happening, but we're not seeing anything super interesting yet. So let's go ahead and rerun this program. We're still in GDB, but make us pause. So one way I can make us pause is by putting in a breakpoint, or just BR for short, and a function name, like main. So this puts a breakpoint at our main function. So when I run this program, it's going to actually stop executing at line 41. So it says there's line in the file doubly, we've inserted this breakpoint at this memory location where this instruction lives. Okay, so now if I hit run here, it's going to start the program and then say, hey, we hit this breakpoint at doubly, and then we're waiting at line 43. So that's what we're doing. So as soon as we enter this function, we'll start to execute, but then before we execute this line of code, which is where we're at here, we're pausing. Okay, so what can we do at this point? Well, we can step forward one instruction, and then it'll take us to the next line. So it just executed this, created our linked list here, and then we can step again, and it'll actually try to jump into this function here, create doubly linked list, and then this function here calls another function, malloc. So we're just stepping through one at a time when we hit S. So it's going to tell us we're in malloc.c. So this function and this library somewhere that we didn't implement. And then we can keep stepping and stepping and stepping and stepping and stepping until, we might see some really inside stuff here. We're inside the malloc function here. So I'm just going to type in finish, and that'll actually, if we're inside a function that we haven't implemented, it'll sort of dive out of that function and then we'll resume at a later point. So right here. So let me just step again. So now we're actually just right at this line here. Okay. And then we can step through. You can see that we're executing these lines one at a time, step through, and so on. Okay. So I'm about to execute this, but maybe I want to print out a value or something just to see what happened here. So I can try doing print new list count, and let's see what happens. If I use print command, and this is actually like Python, the new list that we created in the count, it'll actually tell us the value there is 0. So that's kind of cool. So I didn't have to put a printf here every time if I can just print out the value. Okay, so that's kind of cool. So I can just keep stepping again. I'm at line 27 and so on. Step, and then now I'm about to execute this line and so on. So if I don't want to keep stepping through one at a time, I can also type in next here, which will just jump me to the next function that we've written in our code. Okay, so that'll just go to free. So I avoided jumping into this data structure. Okay, and then I can just type in n or next for, to be short, and then ending program. If I just hit enter, it'll repeat the last command I did. So if I don't want to keep typing in n, I can do that. And then it'll eventually get down to printf and run the program. Okay, enter, enter, keep entering until we eventually finish our program. So it says our program exited normally, and the program's not being run. So if I keep hitting enter, that means we haven't run a program again until we type run again. If I type run again, it'll still have that same breakpoint there from before. Okay, so if I'm done and I hit Q, I can quit GDB and be finished. So then I need to relaunch GDB, add in my breakpoints if I want to run again, and just repeat this process. This time I'm just going to type in next, 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 and you get the idea. Okay. Now something that can be useful to do in a program, I want to show you a few more GDB things. And the Canvas video also has some nice walkthroughs. So let me, type in Q to quit, is to run GDB again. I'm going to put my breakpoint in with main, and then I'm just going to hit the run, and then next, next. And you can type in BT or backtrace, and that'll show you where you are in your program so that you're in the main function. It gives you a stack that shows you which function you're in. Okay, so if I hit S next, I'm in the malloc library somewhere, S, stepping into code further and further. If I type in backtrace again, it'll tell me I'm in the main function and then in this malloc library. Okay, so again, I read this backwards. This is where I was, main, which was here, and then now I've ended in malloc, which we were calling in here. Okay, so that's another useful command. So we've learned about backtrace, which gives us a stack of where we've been, the next command, the step command, Q, and run for how to start debugging our programs, and then print if we want to print out a value. Okay, so that's just a little crash course on GDB. We've got a little bit more in the video, but I just wanted to show you, how you can start building up an structure and inspecting what's going on. Now, what we can also do with this that makes it a little bit more interesting is it can be hard to sort of have the source side by side. So I want to run GDB again with our doubly program, and I'm going to hit Control X2. And when I hit Control X2, you'll see I get a new view here. In fact, I'll do Control X1, and you'll see that I get my source code here. So let's go ahead and do that same exercise. I know this is a bit long, but I just want to show you what's possible, so you know what's possible here. Okay, so I'm going to do BR, put a breakpoint at main. And you'll notice a little symbol here shows up for the breakpoint positioned in the main here. Okay, and here's where our program's going to stop executing. So I'm going to type in run, and it's going to highlight where we are, exactly where we are. I'm going to hit step, and you'll see it'll bring us to the next, within this create doubly linked function that we just created. And I'm going to hit next again, so we move to the next line, the next line, the next line, the next line one more time. And let's go ahead and print out new list count here equals, or just the count here. And you'll see that it equals 0 here, okay, which is this value. And let's go ahead and do next, next, and let's go ahead and step into this prepend function. Step into it, go to the next function, and let's actually see what that data was. Let's try to print that out again. Print new node, next, and let's see what it gives us. Oh, looks like it gives us a struct here. Well, it gives us 0, 0, so the head was previously probably null here, which is interesting. So maybe we haven't actually allocated any memory here. So we're just pointing to null here for our next pointer. I guess that's okay. So let's go ahead and step again. Let's print out, let's go ahead and move. One more thing I want to do is just actually print out this data here of our new node. So print new node and then data. Okay, and we see that this is 487. Again, just so you see what that data was and how to use print. Okay, let's move next and next again. Okay, let's actually print out the list head after doing that. Let's see if it gives us. It actually gives us the memory address here of our head pointer. Okay, that we've just changed it to new node. So if I print out new node, I wonder if this address of our head from our list here is going to be the same as new node. If I hit enter, indeed it is. Okay, so now we can actually use that print command to inspect the memory address in our machine things are pointing to. Okay, so this is kind of cool, I think. And this is about as far as I want to get us here. So we can print out the addresses. So we sort of understand what's going on in our pointers, that yes, we are pointing to something valid that we've allocated memory. We can see where it's actually pointing to, this address here, which is pretty cool. Now again, I might be a little bit lost in my code, so it's just some investigation things I can do. Backtrace and see that I'm in main. Oh yeah, I'm in my prepend function here. And we can see that here. So let's just go ahead and finish. Go next, 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 and then eventually we're going to be finished here. Okay, so we're inside the print function somewhere. Sometimes it gets a little bit wonky. You'll see like what happened here. I just hit Control L, and that'll clear up if you get any noise on your screen. Okay, so again, Control X. It's almost like playing a piano, so you can hit Control X at the same time, and then 2, or Control X and 1. Okay, to give you these different views with the source in GDB. Now, so that's the debugging portion of this. And go ahead and take a break if you want. But if I hit Control X and then 2, there's something really strange that was shown here. Okay, so here's my code. And here's the assembly for that code, which is kind of cool. So you'll notice this breakpoint here. We set one in our main function, right? If you remember, we've done that a few times. Well, I've also got a breakpoint in this second view, which is the assembly code. And this shows us the assembly equivalent of this function here. Okay, so what I'm going to get ready to talk about is how our C code gets translated in this other language called assembly, which is a lower level machine language with very simple instructions that then get compiled, or they have an equivalent of the 1s and 0s. Okay, so here's the memory address where the stuff lives, and then here's the assembly instruction. Okay, so I know this is a lot. We've talked about sort of building our doubly linked list and diving into that, and maybe adding a node, and maybe writing some other functions to remove nodes and so on. And then we've spent some time debugging, right, with GDB and just inspecting what our program's doing interactively without having to write lots of printf functions. So I know that's a lot, but hopefully this built up to something that you see is valuable. Okay, so go ahead and give yourself a pause and then join back if you need. Okay, so if you've given yourself a pause and maybe tried out some of the GDB stuff, or maybe you've gone and done some more doubly linked lists, then let's go ahead and resume here. So I'm going to just type in Q to quit and get into this assembly stuff here, okay? Which is really talking about the life cycle of an instruction, okay? So from C to execution, okay? So already we saw some interesting stuff like memory addresses, right? We have access to that and pointers, and this idea that C gets translated to assembly, okay? So let's just jump right into it. And look at some assembly generated from C. Okay, so that's one place to start, just to see what this mysterious step is, because we have our source program, you know, hello.c or main.c or doubly.c, whatever programs that we're writing. And when we compile them, so the preprocessor, that's what helps bring in all the libraries, goes through this stage, and then we actually get an assembly file, hello.s here, main.s, whatever, you know, our C is with a .s extension. And this is our assembly program text here. Okay, so that was that assembly language that we had. So let me go ahead and just, I just think it's so cool. I have to show you one more time. So if I start, put in a breakpoint in our program, type in run, and then Control X and 2, this is the assembly language here. Okay, so I can even just step through, and you can see where it's stepping through in the assembly language for create doubly linked lists and the different instructions that are going on. And then the malloc library, what's going on. Okay, so I can type in finish to jump out of there. Next to sort of move, and you'll see, you know, there's an instruction here for allocating memory, and then instructions here for moving in the value null, whatever that is, into new list head here, which happens to just be 0. Okay, so again, that's the assembly equivalent that's going on here. Okay, so again, when you're compiling a C program, there's a lot going on behind the scene. You know, there's optimizations that might be going on, you know, transforming C to something. But if we enable the debugging symbols, that was with the -G, we can see inside our programs what's going on. Okay, so again, -G is what we want to really see. Occasionally you get little optimizations and things. The compiler will try to, you know, if you have a variable that you're not using, it'll try to put those in. So you can disable optimizations. Don't worry about this step. The -G is what's really important when we compile our programs, okay? If you want to investigate other binaries, as just an aside, there's a program objdump that will display the assembly of our programs. I mentioned this a little bit before, and it's kind of magic, which is kind of cool, that it shows any program what's going on inside the assembly. Okay, so let's just get into the assembly. Again, this objdump tool is a neat tool to do it, and it shows us stuff that is familiar to us, right? This idea of where a printf instruction is and so on, and the address that instruction's executing, and then the actual ones and zeros are right here that we're seeing. Okay, so here's the memory address, our source code, the assembly needed. So this print command looks like it needs 3 assembly instructions. And then the hexadecimal code. If you translate this from hex to binary, let's just go ahead and do it since we're in this far. Hex to binary. Just so you can see that that instruction, and let's just use a tool like this that we were executing here, BFE0, I'll type in BFE0, 0540, 054000. And if I convert that, this is the actual ones and zeros that your machine is processing, okay? The B and the F usually corresponds to the assembly instruction, so we'll talk about that. And then E005, we can actually see this looks like some sort of value. Maybe it's the ASCII or the text characters hello here. And then 00 might be like the register or where this information is being stored, sort of the variable behind the scenes. Okay, so here's the actual ones and zeros. So there's no more magic there. So you could type this into a computer in theory, or you could type in this assembly, or you could just type in printf hello. So all of a sudden C is not looking too bad, right? Would you rather type in printf and then characters, or would you rather type in ones and zeros like this? Long time ago, this is what you had to do. And then programmers built this assembly language. So you'd write move for moving data, what the data was in some location. And then C programmers came along and said, hey, we'll abstract on top of that. Okay. Okay, so that's the history lesson. Let me go ahead and show you that we're traveling a bit back in time in this lecture. Again, just to show you the magic that's taking place, so you have some understanding of the innards of your machine here. Okay, so we're going back to the 1950s when assembly languages were used. And you might see some kind of famous names here, some of these programmers here that were working on these different machines. Okay, so back in the day, if you go back to your 50s, assembly language is what was used, 60 plus years old at this point. Okay, and it's still used in games. You can talk to me about games if you want. People still write pure assembly code. And if you've used JavaScript, or even most people have used Python, it has its own sort of assembly language called bytecode that's used behind the scenes. So it's still a relevant skill to know about and why it exists. Now, 99% of you might not ever have to write it, but it is helpful to read and debug, okay? So here's just some examples of what it looks like in different languages. If you didn't believe me, in Python, you can import the disassembly library and look at the instructions, okay? So assembly are the bare, metal, very small instructions that are used to implement larger things like print or printf. Okay, so this is what we're going to talk about in our toolchain today, assembly. Okay, but a little bit of hardware history. Again, this is the part you can kind of kick back and relax a little bit at this point. I want you to know the history, the different architectures. Again, I want you to be comfortable with doing the C debugging mostly for this lecture, but let me give you a little history lesson here from our time travel, right? So for a long time, here's our processors 40 plus years ago. It's the Intel 8086, had about 30,000 almost transistors on it. And those transistors are the on and off switches in your machine. So on meaning 1, 0 meaning off. So those are flipping on and off and sort of represent those instructions of those ones and zeros being passed along in your machine. Okay. Now today you have faster machines that have the order of millions and billions of transistors running on them. So here's what a modern processor looks like if you buy one or if you're building your own machine. And the trick is, over time, this is something called Moore's Law. We've gotten more transistors, so more of those little transistors that can flip ones and zeros. So on our machines, and the faster that we can do that, and the more of them that we have, the more instructions we can execute. And the faster we can do it. So over time here on the x-axis, we've gotten more transistors, which means we can do more interesting things on our machines. And roughly every 18 months, we get a machine that's twice as fast, roughly. These days, when you buy a machine, you have something that's known as a multi-core machine. So your machine might say dual core or quad core machine, and that means it basically has more CPUs on it, and that's how we're getting more transistors, by having more CPUs. Okay. The need to switch to these multi-core machines is because having one really big fast processor physically heats up too much and takes too much energy. So we have a bunch of small processors that execute. Okay, so anyway, along with this are CPUs like Intel or AMD or Qualcomm or whatever machine you have particular instruction sets that they understand, right? This CPU, this is your brain of your CPU here, understands certain 1 and 0 combinations, and that's what's known as its instruction set. Okay, so there's an x86 instruction set, which is what this CPU understands. Okay, AMD has one. They're all pretty similar. And this instruction set is what's known as a CISC architecture. So it's pronounced CISC, which stands for Complex Instruction Set Computer here. Okay, so basically it means at the architecture level, the instructions do more operations. So at the hardware level, okay, so it can do interesting things like move data around. There's another set of architectures called reduced instruction set computers who have very, very small instructions. Okay, the instructions are things like add or subtract or load a piece of data or store a piece of data. So they're very simple architecture. Okay, you can learn the language in less than an hour, probably the basics of it. Probably the same with CISC. Okay. And there's, you can look at the actual Intel and AMD and stuff hardware to see what these assembly instructions are, whether they're complex instruction set, CISC or RISC instructions, and how long they actually take. So you can figure out how fast things are on your machine, which is kind of cool. Okay. And a little trivia here, or why would you think complex instruction set computers, I have this little note here, have performance that can be almost as fast as RISC? Any ideas? I'll let you pause and think about it. If you've unpaused and thought about it for a little bit, the idea is everything's really RISC at the end of the day, just really simple instructions, okay? So some other trade-offs here with CISC versus RISC, less important for you to know, but just wanted to show the example of a CISC instruction, which might do like a multiply and store the value versus RISC, which is very simple. We're just loading some address here that happens to be in box. So let's look at this example here. Row 2, row 3, whatever that value is, we're loading it into the variable A. That's the sort of language that you'd be writing your code in. Load B is loading, go to row 5 here, column 2. I guess that's organized, and then you put it in B here, okay? And then you get the product of these two things and then store them somewhere, okay? Now here's kind of a fun one. Does anyone know what pieces of hardware are CISC or RISC that you might own? I'll again let you pause and think about this. If you've paused and thought about it, your complex instruction sets are your general computers, like you're using your desktops and your laptops. And your RISC instruction sets are very simple. They're your consoles, maybe your iPad, maybe your phones are RISC, because they're very simple and they're usually a little bit more energy efficient. Whereas your CISC ones, you can afford to use more energy and have more general purpose computing. Okay, so which is better? It doesn't really matter. There's just trade-offs for the programmers who use them. Likely they're going to be pretty similar these days. Okay. So again, the recap though is that just know that we're generating assembly code from C. It's going to be one of these instruction sets, CISC or RISC, and they have different capabilities. Okay. And computers are overall, which is good news for us, they're continuing to evolve and we're getting more power, which is pretty cool. Okay, so let's look at programming assembly language here. Okay, oh, and I apologize for the white background here if that got you by surprise. But just to understand sort of at a readable level assembly code. Okay, so be able to read what assembly code looks like. Okay, so in GDB, for instance, let's open up GDB because I love it, that you would understand maybe what push means, or this idea that it's sort of pushing some data on a stack or moving some data around or subtracting, just so you're not completely afraid of these instructions. You could sort of infer what they mean. Okay. So why learn assembly? Then you know exactly what the machine's doing. Some of you might go on to work on compilers or maybe sort of robotics. It could be a really good use case, or if you go into security and sort of need to reverse engineer things, this becomes particularly important. Okay, occasionally it's helpful for finding bugs as well, and you just understand how the compile cycle works, okay? Which we want to know how things work in this class. Okay, so let's look at a program in assembly here, and here's a first example. I love this tool. This is going to be your tool for really learning assembly, but it's called Compiler Explorer. It's by a gentleman named Matthew Godbolt. Probably has the coolest name I've ever heard, Godbolt. That's his real last name. I've met him. He's a nice guy. And he deserves a cool name. But what this tool is showing you is on the left, your program, your C program, and on the right, the assembly equivalent. Okay, so if you can see the colors here, they correspond, and as you highlight over something, it shows the corresponding assembly here. Okay, so here's move. Here's what it looks like to store the value 57 in an integer. Okay, and this is a long type of integer, so a big one. Okay, and so what we're doing here is we're storing from some source here the value 57 into a destination. And this is some memory address on the right side. Okay, I'll talk about that in a moment. Okay, so that's what we're seeing. So the push commands, they're like our stack. So we're actually pushing Q, which stands for quad word, which is just another fancy way to say 8 bytes of data onto a stack. Okay, and then we're moving some data, again, looking at this suffix, Q for quad word, from some source, that's the first operand, that means this thing, first argument, to a destination, that's the second operand, to this memory location. Okay, so push Q, we're pushing a quad word onto the stack, and then eventually we return some data here. Okay, so we're returning from a procedure to the address on top of the stack here. Okay, so a few things here. So we have main. Here's our main function. We're adjusting the stack. So something's going on here where we're moving data around. Storing 57 in some location here. And we have a stack here. We'll talk a little bit about what the stack business is. And an offset from that stack. And then we're moving 42 in another location. Okay, so we're returning the value of 42. Popping some value from our stack here, so RBP, that has some meaning, and then we're returning from this function, right? We return from our functions. Okay, so is this coming back to you? Well, maybe, depending on what we've learned about, but let's do a little bit of review here, okay? We could run this in objdump, just as a side, but I like Compiler Explorer. So let's review our assembly here, okay? So again, with assembly, we're using different instruction set architectures. That was like our Intel x86. That's specific to our machine. So these instructions, push Q, move Q, move Q, move L, pop Q, return, and so on. And as assembly programmers, we think of things in terms of registers, instructions, data types, and memory address modes. That's it, just 4 things. The whole language, you're going to learn it in the next 20 or so minutes while we wrap up the entirety of assembly language, okay? So here's registers, they're like variables. You can think of like cache register, you store something in it, but here you're storing some value. Okay, so anything that starts with a percent sign is a register. That's just the syntax. The instructions, those are the commands that you're executing, how you do stuff, push data around, move data around, and so on. The data types, and this is just the suffix of a command. So quad word, which stands for 8 bytes. L, which is 1 word, which is 4 bytes. It's a little bit weird syntax, quad word and word and double word, you'll see. here, and then the memory address mode. So if it starts with a $sign, that means just a literal value 57. Okay. If it has parentheses around it, this means we're actually indirectly accessing some memory. Well, how did we indirectly access memory before? We used pointers. Okay, so if you see parentheses, that's your pointer. You're dereferencing some address and then subtracting 8 from it, which is kind of interesting. So some of our pointers, we see how they're related to C. Again, you don't have to memorize this stuff. I just want to show you what's going on in the machine a little bit. Okay, so registers, these are our variables. And we have 16 general purpose registers in assembly. That's what I want to show you for here. So in assembly language, we only have 16 variables that we can use. They have specific names like RBP, RSP, and so on. And a fun one, RIP. No, it's not that morbid, but this is the register instruction pointer. And this tells us sort of where we are in our program, what's the next instruction that we're executing. Okay, so again, we're getting a little bit lost at this point, maybe in our assembly, but the instruction pointer, it's basically, you see where this caret is? The instruction pointer is saying, hey, you're going to execute the next thing that's at this address. Okay, right? Things in our machines live in addresses, which happens to be this command, move, where you're moving data around. What data are we moving around? Well, we're moving 0 into our head here, okay? And our instruction pointer keeps track of where we are. So if I step again, our instruction pointer says, hey, you're here now. If I step again, your instruction pointer says here. So this register in your machine, right? This information has to be kept track of somewhere. What instruction you're going to execute next. Okay, so that's all that's doing. So here's your general purpose registers. We were just talking about that instruction pointer. That's not one of them, but you have 16 other registers that you can sort of use like variables. They have specific uses or conventions. You don't have to follow them, but you probably should, otherwise something wrong might happen. Like you might point to the wrong data, but they have certain conventions. Like there's a register, which again you can think of like a variable, stores the return value usually, okay, or the accumulator. It accumulates values. So they call it the register, the accumulator register here, RAX, okay. And you can actually, what's pretty cool is with each of these registers, there's 8 bytes, which means 64 bits. But if you only need a few of the bits or a few of the bytes here, you can actually change the prefix here. Most of them start with R for the 8-byte registers. But if you just do EAX, that just addresses the first, or rather the last 32 bits of this register here. If you don't need all 64. So right when you're creating ints versus longs versus chars, those data types in C have different types. Well, you try to use the least amount of bytes as possible. Okay. So here's just an example of that in a picture. So the register RAX, 64 bits, so 64 ones and zeros here, or 8 bytes if you prefer to think of it that way. Again, a byte is 8 bits. So 8 bytes, 8 times 8 is 64 bits here. If you only need 32 bits of information, because you're storing a smaller number, then you can just use register EAX and store some values there, okay? So that's one way we sort of get around with, I told you this scary thing that we only have 16 registers to store information in. And you might say, well, Mike, I have way more variables than that. Well, there's some clever tricks where we can sort of move things in and out of registers and store some information around, which is exactly what's going on here. Okay, so let's talk about instructions a little bit. Okay, so we know we have registers, which are like variables, and instructions are how we actually do the work. Okay, so here's sort of the anatomy of an assembly instruction. Okay, you have an opcode, that's the instruction or the work that you're going to do, and then some arguments here. These are the operands. Okay, so these are your parameters into the function. Okay. So here's your opcode, move q. So you're moving some data around, and your operands list here. So that moving from the source to destination here. Okay, operand 1 and operand 2. Okay, and that's it. Okay, and the code that I'm going to be showing you is what's known as AT&T style. Yes, that is the phone company. A long time ago, they did a lot of cool research stuff in programming. Now they just send me bills, but AT&T a long time ago. worked on some of this programming language stuff. So this is the AT&T style assembly language, which basically means you have a source for your operand list and a destination. So that means I'm going to move this data, this value 57, into a destination here. So somewhere here, okay, wherever this memory address is. So again, in assembly, we're just thinking about moving things at the level of values, like the number 57, into a memory address, okay? There's other styles that you use, but this order is important. It's always source to destination in AT&T style. Intel actually flips it around. Okay. Okay, so first instruction for us to learn is move. It's sort of a simple one, but move Q, which is about moving data from a source to destination. And that's exactly what happens when we're assigning a variable. So let's go ahead and look at that Godbold example back here in Compiler Explorer. So I had long here. Let me make it a little bit easier for you, maybe. There we are. Long I, and it's got this slightly yellowish tint here. So I'm moving some data, 57, from source into destination here. Okay, that's all that's going on here. That's all the takeaway I have here. That's a simple assembly instruction for you. We learned that the suffix here, Q, has some meaning. That it's a quad word. Okay, so how many of those bytes are we using in the register? Well, we're using a register there. Let's check. Yeah, this RBP one. Okay, so this memory address. We're figuring out where that address was. We're dereferencing. That's equivalent to putting a star, and then we are offsetting 8 from that address. I think if I actually highlight over it, it might tell me where we actually are. So at this address here is where we're storing the value 57, 0x, FFFFF, and so on, 8. Okay. Okay, so let's continue on. So we're moving a quad word, as we talked about, so 8 bytes of data. We use a suffix here. And that's how we get our data types in assembly. Okay, so here's the equivalent in C, right, that we learned. And here's the suffix we use for the assembly command, depending on how many or how much information we want to move around. Okay, B for byte, W for word, that means 2 bytes. A double word is L, so 2 times a word, a double word is 4. A quad word, how big's a word? 2. So a quad word is 2 times 4, that's 8 bytes of information, okay? And that's how we get our data types in assembly. We just have numbers here. Based off the amount of information we're moving around, okay? Anything that's a pointer is 8 bytes for us on a 64-bit machine. So we're moving as many as 64 bits around, okay? Now these names are sort of terrible, like word is a weird sort of data type. In double word, you'll sometimes see DWORD or DWORD. But that's just sort of a historical thing that we're stuck with for how we name some of these data types, right? We didn't name them int or long or anything, but we have word or double word for data, okay? Okay, so more suffix stuff to pay attention to. The nice thing about assembly is all that it's going to do, or everything that the assembly instruction does, is in the name of the command. So in a move command, you start seeing other letters here, and they sort of consistently show you what the command's doing. Okay, so here's a weird one. You don't have to memorize it, but we're going to move some data here. If we need to, we'll add zeros. So if you have a Z, that's usually what it means. And the BL is for like a block. So basically, you're going to move, or B is actually the size of this register. So B, if I look back here, means we're working with 1 byte. L was a word, so this is, well, let's look at our chart here. 4 bytes, a double word, excuse me. So we're going to move something that's 1 byte, so something that's really tiny, like a 1 byte instruction, into another register that's bigger that can store 32, and then zero out all of the other bits that might have been here before. Okay, so you don't have to memorize this stuff, not in this class. If you take this with 5600 with me, we'll review again, and we'll do a little bit more deeper dive where you actually get to write some assembly. But it's not too scary, right? You sort of learn what these commands do based off of how they're named. And that's how we just take something like this and break it down into smaller pieces, right? So you've learned we're moving data around. We have registers, a source, and a destination, and that's all that's going on behind the scenes. Okay, some other assembly things. We have jumps, right? This is how you move around in your code. So assembly commands that start with J mean you're jumping somewhere, and you might jump somewhere if it's not equal to a value. Okay, so what's the command before doing? This is a compare. You're comparing two quad words for this value 4096 to whatever values in this register. If they're not equal, so if whatever's not stored here, you're going to jump somewhere. You're going to jump to .lbb1_1. Okay, so you say, hey, Mike, what the heck's that? Well, this is a label. This tells you the location of where you're going to jump to, okay? I'll show an example in a moment, but this is how loops and if statements and so on are implemented. You're comparing some values, and if some value is not equal or less than or greater than equal, you jump somewhere else in the code, okay? And each time you do these operations, like when you're comparing a value, there's behind the scenes in your computer, there's a little scoreboard, and it contains all these condition flags. And it says, and it always tells you what the score is in your machine. So again, it's just a giant scoreboard. If you want to think about a sports stadium, it has a giant scoreboard with all the conditional flags, and it'll tell you what the result of the last operation was. Was it 0? Did the sign change? Did you create a value that was too big? That's where the carry was, you know, some really, really big number. And these bits will flip 1 or 0 based off of that. And based off of that, you can figure out what the result was of some operation and where to jump, okay? So just know, again, the takeaway that there's a giant scoreboard with all these conditional flags that tell you where to jump in your code, okay? Here's the jump instructions that you can do, right? Just jump somewhere to address 1. Jump if two values are equal, jump if they're not equal, and so on, okay? So you're saying, you know, Mike, why are you showing me this? How do we pragmatically use this? Well, let's look at this example here. Jump if equal, so you're trying to check if two values are equal, and it's going to check the 0 flag condition. Okay, so how does that work? Well, what happens is when you do the comparison between these two values here, 4096 and whatever happens to be here, if they happen to be equal, the 0 flag will toggle to 0. And then if you have a jump if equal here, it'll jump to wherever this label is. If the jump where not equal is, it'll jump wherever this label is, okay? So that's what it's doing. So every assembly instruction that you execute, there's also a scoreboard keeping track of what happened mathematically after that command. Was there a 0 generated? Did the sign change, etc.? Okay. Okay. Last things I want to show you with assembly is that our assembly instructions have different ways to access memory, right? We've already looked at this in C a little bit, right? We've learned about ampersand, we've learned about pointers. And there's different ways to, in assembly, talk about or access memory in that same way, okay? So we can directly address memory. Okay, so here's some examples where I use this specified value here, 172, and I move it into a register. Or maybe another register has a value, and I move it to another register. Or again, directly specify the memory address. Remember how we talked about how things start with hexadecimal values? So 0x172, whatever this memory address is, move it into this register, okay? And that memory address stores something, okay? And then likewise, I can indirectly access memory. Okay, so that's sort of like a pointer. What did we do when we wanted to indirectly access memory? Well, we dereference the value. And in assembly, we use parentheses to do that. So let's just look at this first example here. If I have a register here, and it stores an address, and I want that actual value, I dereference it. This is equivalent of putting a star in front of it, but I use parentheses, and I move it to this register here. Okay. I can do that similarly here. Here's how I would implement arrays. Okay, where I would dereference whatever's at this memory address, and then the offset here in bytes, 172. So whatever happens to be at that value, and then move it into a register. Okay. Let me see if I can do a quick, because the arrays one is kind of interesting. If we do this in Compiler Explorer, let me open up a new version of Godbolt here. just so I don't change that example. And let's create an array like this. And let's access I at 3. Let's see if it does anything interesting. Let's see if we can actually see that. We may or may not be able to. Our compilers are pretty smart. Let's see. Let's see if I can do this. Sometimes it's smart enough to just figure out what this memory address is. I want to see if I can get the offset for you. Let's see. Put in some values here. Okay. Yeah, we are getting it. So here we're moving the value 7 into, well, wherever this memory address is, and we're offsetting it by 1600 here. Okay. Don't worry as much about the computation here, or why it got 1600. But we could actually, again, compute where that memory is here. Okay, so just wanted to show you that offset, or indirectly accessing something, right? We're dereferencing with our arrays, so you see the parentheses here, and then we have an offset. Okay, so here's the C equivalent to the move Q instructions, like we looked at. Just moving a value into register, that's like signing a variable. Dereferencing with the parentheses, so moving a value into a memory address, just reassigning two variables, dereferencing, again with the parentheses, so your source here, REX, that's on this side, and then you're dereferencing, so star P, the parentheses here. And then likewise the other way, so storing in temp the source, star of P, into RDX, which is temp. Okay, there's other ways you can get further into this by doing sort of indirect addressing, and it just kind of gets a little bit further and further. Okay, so this is how you sort of use structs. Okay, let's see. So labels are one of the other topics that I mentioned. So how do you sort of jump around in assembly? So if you have a for loop here, for instance, let's just look at it on Godbolt. Just such a nice job. I'm showing you what's going on. A loop here. This for loop here in this sort of bluish tint, if I highlight over it a couple times, or the yellow here, you'll see that there are things that start with dot here and then end with a colon, so L3 and L2. They're not very intelligently named, but these are labels for where to jump to. So if this condition is not met, that is, if I is not less than 10, we jump to L2 here, okay? If it is met, then we stay in this loop and we stay in label 3, okay? And we just keep adding ones, add instruction to a particular address, okay? Which is what we're doing here, okay? I don't need you to understand all of this, but I just need you to see that there's a way to sort of jump around to labels in our loop, right? So if this condition's not true, we jump somewhere else, right? Which we jump to line 7 and start executing from here, okay? So that's how labels are utilized in conditionals. Okay. Last topic on assembly is procedures and functions, and this is something that's useful for you to understand because it relates to some of the memory stuff that we talk about, okay? So this is how procedures work. Procedure is just another name for a function or a method, depending on how you've learned about it, right? So it's something when you call a procedure, so function or method, you're passing control around, so you're changing where the program's executing from, and then you want to return back to where you're called from. Okay, you're passing data around in the form of arguments, and you might be managing memory. Okay, and then the assembly stuff you don't have to manage as much, but you know that you're using or trying to do things efficiently. Okay, so in x84 there's something known as we have a stack. Remember, our programs are just a giant byte array, but it is divided into regions in a way. Okay, so there's your stack memory and there's heap memory. Okay, so let's just think about our stack memory again as this giant byte array. Okay, and here's what our program actually looks like when you launch a program. You've got the program stack here. It's divided into several different regions, right? When you write a program, you've got your instructions here. You've got some literal values here, like when you type in a string hello world. You might have some other data that you've allocated, like an array with values in it. Your heap memory, which can expand sort of upwards here every time you use malloc. And then your stack data, which every time you allocate, adds on top of the stack here, okay? Each time you do something. Okay, so with the stack data structure, which we learned about a little bit, we can perform two operations, right? We can push data onto our stack rows, and pop data off our stack, in which we remove information. Okay, so let's sort of orient ourselves. And this is a little bit of a confusing thing. So the bottom of the stack here is this stack memory here. That's what I'm talking about here. Okay, it's got a very high address. Okay, so it's sort of organized in this manner. And at the top of our stack, our program stack, just starts from address 0. Put a bunch of instructions here, some literals, any data that we've allocated, and then we have our heap. Okay, and the addresses are growing up. Okay, so as I do stuff, this number is getting bigger in this direction. Okay, but when we do things in our program, our stack here, okay, adds on top of it in this direction. Okay, so that means the top of our stack is approaching address 0. Okay, so here's the bottom of our stack here when we call a procedure or a function, and it grows in this way. Okay, bottom of the stack, we push stuff on top of the stack, keep pushing it on top, and then we pop stuff off when we're done with it. Okay, and then hopefully it doesn't, if we put too much stuff on our stack and it collides with our stack data, does anyone know what kind of error we get? It's our favorite website. I'll let you pause and think for a moment. But we get a stack overflow if our stack grows too big. Okay. So again, hopefully our stack grows down, but hopefully not into the heap. Otherwise, we get an error. Okay, so when you observe things in your assembly like -8 RSP, right? This is our address, and we're offsetting 8. So if I have a really big address here, let's say it's 1,000,000, and I'm moving 8, I'm moving down the stack here in the stack memory. So that's how you know it's located in the stack. Right? It's not a specific address, it's just moving down. It's an offset from there. So we're growing down in addresses towards 0. That makes sense because we know how big our program is and our data that we've allocated when we start our program. So this is sort of fixed. Let's say this number is 1,000 here. Okay, but we don't know how big this is going to get, so it just sort of grows down. Okay, what was RSP again? Well, this is a stack pointer. So we have one of these assembly registers that points to the lowest address in our stack here. It's the lowest because, again, we start from 0, and that represents the top of the stack here. Okay, so here are some of our general purpose registers. We care about this one, RSP. Keeps track of where the stack is. So if we do some operation like push Q, what that's doing in assembly is it's pushing some value on the top of our stack. Okay, so here's what happened. I pushed and I pushed it on top of the stack. I've done this a few times, and then our stack pointer is updated, so it's always pointing to the top of the stack. And this is the same thing you're doing in your homework when you implement a stack. You're going to have a sort of pop operation that pops off something at the top of the stack, okay, which is what pop does. So we push something on top of the stack. This is our data, like when we write a function, and then we pop it off, okay? And then, we just have garbage there. It's just not being used, I guess. It's whatever the old value was. And then we have our stack pointer point again to the top of our stack here, okay? Okay, so that's how things work. So again, when we're executing functions, functions are pushing and popping data off of our program stack. Okay, and that's where values come, and that's how it's maintained. So now you know the assembly of how it's maintained, which is pretty cool. Okay, so that's a lot. If you want to write a first assembly programming program, this is how you would write it. So this is kind of an optional exercise, if you like. And then this is how you would execute it. Okay, it's a little bit of a different tool chain, but this is what an assembly program looks like. And then I just wanted to show you something cool because, again, you might be thinking, what's the use of assembly? Why use it, etc., etc. But here's a game, and I always give the punchline away, but it was written in 60 or 96 kilobytes of information. So if you don't know what a kilobyte is, or just for scale, a kilobyte, a floppy disk can hold 3 megabytes of information, if you've ever seen floppy. CDs hold a couple 100 megabytes. Your hard drives are, several hundred gigabytes or maybe a terabyte. Kilobytes, this entire game here, I'll let it play a little bit, is written in enough assembly code that you could fit it in a single email, which is pretty cool. So there is a lot of power in this assembly stuff where you can be very optimal. And I would say it looks pretty good, right? For people who play games, you would maybe say it looks pretty good. And for other people, if you don't play games, just know that, if you could send this thing that's executing here in an email, that's pretty cool. And assembly is very, very, very powerful for this, okay? So just some cool stuff with assembly, okay? So with that, you have your in-class activity and your lab, which we'll talk about during the live session. And again, just the final message. There's more optional stuff on assembly, another introduction or another way to look at it. But your takeaways, again, are, let me zoom up here, focus on the debugging stuff. Know that you have another data structure, the doubly linked list, which we slowly built up. And just understand that this assembly language, it isn't scary, but it is the human readable version of what the machine is doing, right? The ones and zeros, which we looked at, okay? Okay, so I hope you enjoyed that sort of peek into assembly. Again, we understand how to debug, we built some skills there, and we understand that the operating system is sort of managing all these processes and how they're running, and that we can interact with it with our debugger, okay? So that's it, and we'll see you in class.